Alright, now we're in Chapter 10. This is 2014. First PowerPoint for the new year. And it deals with periodicity, which basically is kind of a review of the periodic table. A little more in depth, but so it's a good review of the physical properties of elements. Chapter 10 talks about the structure of the periodic table. Quick slides. First, it was organized originally by Russian Dmitry Mendeleev. He ordered it by atomic mass and column or vertical columns with similar properties. You can see on the picture on the right, he had his elements: sodium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine is in the second row. Oh no, half lane, sorry, not sodium. And you can see there's some missing pieces, but a good start for the periodic table. Here we have our current model. It's ordered by atomic number, which means the number of protons. And there's 8 major groups, and the rows are periods, and periodicity is the recurrence of some same pattern in the periodic table. So that's why it's called periodic table. You have different blocks depending on the orbitals. You have the S block, the D block, the P block, and the F block down below the lanthanide and actinide series. There's only a few instances that the atomic mass differs from the next atomic mass, but majority of the time the mass does increase as the number of protons increases. Alright, physical properties. So this is the majority of the periodicity. So first we have the atomic radius. This is period 3. You can see as you go from sodium to argon, the atomic radius is decreasing. This is because of the number of protons is increasing. This radius is kind of staying the same because you're on the same period. So they're all on the same energy level. So as you're increasing protons, your attractive forces are basically attracting the electrons closer and closer together, causing the radius to get smaller. Okay, the ionic radius is a little different. It does decrease as you go across, but it depends if it's becoming there's only a big jump between the cation and an anion. So you can see sodium to silicon are cations, and the radius is decreasing as you go across. Same concept, more protons, it gives the attractive forces between the electrons and they pull closer. But there's a big jump to phosphorus, and that's because they are gaining electrons. So the protons is still increasing, but you're gaining more electron, causing the electron cloud to be higher. But then as you go across to chlorine, it does decrease because of the number of protons. So the cations all have 10 electrons, and then all the anions have 18 electrons. More protons means going to have a smaller radius. So cations are smaller than the atoms themselves. That's because there's less electrons, so there's less electrons to be pulled in to the radius. They lose electrons from the level, thus the more protons they have, the smaller the radius they're going to have. Anions are larger than the original atoms. That's because they're gaining electrons. Thus you're adding to the level of the energy level, and then the protons becomes less than the electrons, therefore a larger radius. So the electrons outweigh the protons, giving you a bigger radius, and then the cations are the protons outweigh the electrons, giving you a smaller radius compared to their atom. Alright, check out number 2, homework question. You want to look at the periodic table and predict and explain the relative size of the atomic radii of lithium and fluorine, and then predict the relative sizes of lithium atom and its ion, and comparing the oxygen atom to its oxygen ion, oxide, And the same thing between nitride ion and the fluoride ion. Compare their relative sizes. So basically, which one's smaller and the reason why, which one's larger and the reason why. All right, melting points. Melting point across the period really depends, again, on their structure. So if it's metallic, if it's molecular, and then what size they are. So you can see as you go to sodium, magnesium, aluminum, they are all metals. They are increasing. That's because there's more electrons in the out in the outer shell. So there's more electrons are delocalized, thus giving you a stronger metallic bond. More electrons, more delocalized electrons, therefore it's a stronger metallic bond, so it's tougher to break. So the intermolecular forces are tough to break, therefore a higher melting point. Now the difference with silicon, it's not metallic, it's actually a metalloid, and that's why it's a giant molecular structure. It's very structured, meaning it almost looks like a crystal, but almost acting like a diamond. So the melting point is very high. It's covalent bonding, so it's strong, and it's organized, so it's even stronger. So that's why the melting point is very high, and it's because of its structure, giant molecular. Now, other non-metals, you can see they're decreasing relatively, and that's because of the weaker van der Waals forces. So since the size of them, the radii, are getting smaller, the intermolecular forces become weaker, and you have a decrease in melting point. The melting points become lower and lower, so it's easier to break those intermolecular bonds. So everything goes back to atomic radius. So metals, more electrons, higher the melting point. The metalloids like carbon, boron, they're giant molecular, so they have higher melting points. And then with the nonmetals that are simple molecular, the smaller they are, the weaker their van der Waals forces are, therefore they're easier to melt. Electrical conductivity. This is pretty basic. Metals conduct, nonmetals don't. So why does the metal conductivity increase as you go across from sodium to aluminum? That's because, again, more electrons, therefore higher conductivity. And then in nonmetals, same thing. There's no delocalized electrons at all, so there's going to have very, 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 very non-existent conductivity. You can see that in phosphorus and sulfur and chlorine and argon are gases are fine. They're not going to conduct electricity. Silicon is a metalloid. It does conduct a little bit, and that's because of its structure as well. All right. Checkup number 3. Why does sulfur have a lower melting point than silicon? Why does sulfur have a higher melting point than chlorine? Why is magnesium a better conductor than phosphorus and sodium? Alright, last one, ionization energy. So, we talked about this a little bit when we talked about orbitals. You can see at first glance, ionization energy basically has no pattern, but it does. The s orbitals, which are sodium and magnesium, it takes more energy to take away from magnesium than sodium because of the full s orbital. Sodium only has 1 electron in the s, magnesium has 2. It can only hold 2, so it's tougher to take that electron away from magnesium. So it's kind of easy to break this apart into their orbitals. Now you look at lithium, silicon, phosphorus, sulfur, chlorine, argon. Those are the p orbitals, and as you go across, it's harder to remove, which makes sense, but you can see there's a dip between phosphorus and sulfur. Again, that is because you always can fill 1 electron first in the p orbital. There's 3 different p orbitals, x, y, and z. So once you fill an electron in each of those p's, aluminum, silicon, phosphorus, then once you get the sulfur, that 1 electron goes into one of the p orbitals to pair up. So the p, when it's phosphorus, when it has 3 electrons, it's going to take a little more energy to take that 1 electron out than when sulfur has a pair in the p orbital. And again, as you go across the chlorine argon, it takes tougher and tougher to remove the electrons. So there is a little pattern, and it's based on the p orbitals and the s orbitals. And the main reason why it causes the dip is because of shell shielding. Shell shielding, which basically just means it shields the electrons, which then it takes easier to remove. And that's only between magnesium and aluminum and phosphorus and sulfur. All right, last question. What is the general trend in first ionization energies across period 3? Explain why aluminum has a lower first ionization energy than magnesium, and explain why sulfur has a lower ionization than phosphorus. See page 166, predict the missing value for the first ionization energy of selenium, and explain your reasoning. All right, if you have any questions,